Okay, so we're going to call this section 4.1. It's a review of law of sines, which you might have had in geometry, or if you remember from geometry. So what law of sines allows us to do is solve triangles that are non-right triangles. We call them oblique triangles. Okay, so oblique triangles, just as a reminder of this term, are either acute, which means they have all three acute angles, or obtuse, which means they have one obtuse angle, if you remember that. Okay, but not a right triangle. Now, there are some cases here I'm just going to share with you briefly on when you can use law of sines. So, you can use law of sines when you have an angle, the side in between, and another angle, or you have two angles and a side. And the other case is the ambiguous case, which we are not going to do. I don't know if you remember this or not, but there was a code like this where if you read this backwards, it's bad. Okay, so case number 2 we're not going to worry about because it's the ambiguous case. Then we do have other ones. If I have the side and the angle in between the other side, I have to do law of cosines for that, if you remember. And then the other famous law of cosine one is this. So 4.1 and 4.2 are kind of linked. But if we go through this, what we're going to focus on today is situations that have this here. Okay, and that's going to use law of sines, just for a note for later. These two here, okay, which we're going to get to in the next section, use something called law of cosines, a little more complicated formula, but again, you'll have your cheat sheet to go with, all right? So let's look at law of sines. Here's how law of sines is defined, if you remember. Okay, there's a relationship between the angle and the opposite side, so I'm not a big fan of this. I'm going to make this big A, big B, and big C. It's kind of how we learn it. And the reason that's kind of important is there's a relationship between the sine of an angle and its opposite side. So if you look here, these letters are important. Big A and little a. Do you see it? Big A is here in the corner. Little a is across from it. Same thing here. Big B is going to be here, and little b is across from it. So the relationship matters. And then, of course, not too much different, but C's here and little c's there. All right, now, what we do is we write it this way to show you all three ratios are the same. We're only going to use 2 at a time. Okay? And it just sort of helps us format it a little bit. So let's see if we can solve example 1. Example 1 says if we have this here, I'm going to draw an ABC triangle. A, B, C. So I'm going to call it big A, big B, big C. And A here is 64. C is 80. C up here is 82. And again, the order of this doesn't matter. You just draw A, B, C. But what does matter is that 14 is right there, opposite C. Okay? And then it's going to ask me to find the missing sides. Now, when you have a situation like this, then this is the important relationship right there. That allows me to do law of sines. So what I do is I build that ratio. So I say sine of 82 over 14 equals, the first one I'm going to find is that one right there because it's opposite that angle. So then I can build it as sine of 64 over x. So if I go ahead and do that cross then, okay, what's going to happen here for that one is if you do it, I'll get 14 sine of 64 divided by sine of 82. If you do the cross, you know, divided by the cross, you don't know, depending on, that's going to make little a. Actually, I should have done that, I guess. Let's erase this just to get used to it. This is little a, making this little a. That's better instead of x. That makes little a, which is a side. Little letters are sides, big letters are angles. 12.71. Okay, now, the other one I can find quickly, sort of, is angle B. How do I find angle B? I don't need to do any trig for that. Do you remember the triangle sum theorem? So 180 minus 64 minus 82, right, is going to give me a big B of 34. Now, the last thing I got to find then is I got to find over here, I got to find little b, right, opposite there. So how would I do that? Now, this is just from my engineering world. They always taught you should use what's given all the time. So I'm not going to use what I found. I'm going to use the given again. So I'm going to go sine of 82 over 14. That ratio is equal to, now also this ratio, sine of big B, or I'm sorry, sine of B, which would be sine of 34, yep, over little b. If you do this cross, again, the cross you know, divided by the cross you don't know, that's going to give me little b is equal to 7.91 if you want to try that on your calculator. All right, and then what I've achieved there is I've achieved solving the entire triangle because I know all 6 pieces. Okay. The second one sets up the same. You would find the missing angle, find the two sides. So we're going to do that. We'll go over that in class. This is something called the ambiguous case. The ambiguous case deals with this. And there's a situation there where you can have two different triangles developed. We're going to skip over that for now. But just know that two sides and an angle can create some different challenges for that. Last thing I want to go through in this section as a preview is how to find the area of an oblique triangle using sort of a code here. You want a bunch of formulas that uses big letters and little letters to do it. So let's see if we can apply that here for number 6. Okay, and it's a nice shortcut, and you'll have access to these formulas. So it says the area of a triangle having two sides, lengths 8 and 12, and an included angle of 35. So I like it better when they kind of label them, but what does included mean? Oops. What does included mean? It means in between. So when you build this, I'm just going to build basically these two. I'm going to call this 12 and this 8, and I'm going to call this 135. That is not a great example, so let me just redraw this real quick. Not that scale matters, but if I had looked ahead, let me make it bigger than 90, something like this. 8 and 12, and then here would be my triangle where this would be 135. So again, that first picture would have worked too, but let me give you one that kind of makes sense. You want to find the area of it, okay? So for this one then, depends how I label them, all right? So I'm going to go through and label this A, B, C. Again, the labels aren't important, but it will help me sort of help you through the formulas up here. If I choose that, do you see if I choose that setup, I'm going to use this formula right here, okay? Because C is the angle that's given. Again, there's no magic to that. It just might help you put it together, but it's a good review of which sides are which. Do you agree then that this is little a, this is little b, and this is little c? Okay, so this is what I'm going to be doing. And again, if you have two sides and the included angle, I can find this area. So what would the area be for this? Okay, it would be 1/2 the length of little a, which would be 12, times the length of little b, which would be 8, times, that's what that means, times the sine of 135. Now there's a development of this where if you dropped a height, which is really part of the area of a triangle formula, the sine finds that for you, so this is just a shortcut. And then if you would plug all that in all the way across, you would get an area approximately equal to 33.94, in this case, meters squared. Okay, so again, these formulas aren't super important, though just know that the angle should be the included angle between the two, and then the A and the B are sort of interchangeable. So, all right, so that's the lesson for today. We'll conclude doing some of these